All right, so talking about the item is fixed effects fallacy that Tal brought up in his Tal Yarkoni brought up in his keynote last year, and just to give you guys a refresher for those of you who weren't there, if these will advance. There we go. So fixed effects model. A fixed effects model would be something along the lines of a clinical question like what's the effect of some amount of drug, 3 grams of aspirin, on LDL levels. You've got your response in Y, the LDL levels. The treatment is your aspirin, and the effect, the parameter that we're estimating, is the change in LDL levels over the population, comparing two populations to each other. So comparing the control population to the treatment population. In fMRI, this might look something along the lines of looking at our response is going to be the bold signal of the brain. These could be voxels, vertex, ROIs, whatever. And our effect is maybe we're looking at a 2 back versus 3 back. Everything we say here for effects applies equally to contrast. They're mathematically equivalent. But if you notice here, we're not comparing two populations anymore. We're comparing two sets of individuals that are sampled, or comparing sets of individuals sampled from a population. And in that case, so you've got your population, and your research subjects are randomly drawn from that population. Yeah? No. Apparently we can't draw any subjects, so we're going to have a hard time conducting a study. There we go. There's your research subjects. So they're random sampling of that population, and that random process has to be accounted for. That random process creates additional variance that you have to account for in your model. And everyone knows this. Pretty much every neuroimaging analysis package is going to allow you to account for subject level effects. But what if you weren't interested in a 2 back versus 3 back contrast? What if you're doing, there we go, different question, something about, to quote Tal from last year, happy pandas versus neutral pandas. And you go on Google to get your stimuli, and it turns out there's populations of happy pandas and populations of neutral pandas. And if you want to compare those entire populations, your subject's going to have to be in the scanner for way, way, way too long. I was going to make GIFs to scroll through all of the panda results, but it broke my laptop, so sorry. There are lots of panda pictures. So here we've got lots of levels of sampling. We've got individual happy pandas drawn from a population, neutral pandas drawn from a population, and subjects drawn from a population. And now if you're with me when I'm saying that drawing subjects from a population is a random effect and variance that you have to account for, then you also have to kind of admit that the item level effects, these random effects of items, the process of sampling those pictures from those two classes is also something that you need to account for. And so this gets you to the realm of crossed mix effects. So you've got random effect of the subject that is already accounted for in most approaches, as well as a random effect of item that is really only very rarely modeled. And modeling the random effects at these two levels simultaneously is computationally challenging. We've talked about a couple of packages already that'll do it. LME4 is one that's probably most commonly used. There's also packages in Julia. Doug Bates who wrote the LME4 package, went on to write this package in Julia. And then there's also a package that Tal released for estimating these mixed effects models at the ROI level with a Bayesian approach. But again, this is only feasible at the ROI level. And if we want to be able to do these mixed effects models accounting correctly for the variance contributed from our item sampling process at the voxel level, we need to come up with something else. It takes, as Tara was mentioning, it takes a long time to fit these models at the voxel level. You could just broadcast all this stuff out to a cluster. That might work if you're then not sure about how to calculate the significance, and you want to do some permutation approaches, bootstrap approaches. That's going to really just become completely computationally infeasible unless you're willing to dump a whole bunch of money into AWS for every iteration of your analysis. And so MELD, mixed effects for large data sets, is an approach that we've been exploring to make it computationally feasible to get these voxel level results in a reasonable amount of time. And so the approach that we take with MELD hangs on a singular value decomposition. And first we are correlating the independent and dependent data. So correlate your neural data with your predictors and do a singular value decomposition to identify the shared space, the space that's going to maximize the covariance between your independent and dependent data. This is just an illustration of what you do with a singular value decomposition. You're taking your data. In this case, it's one neural map per trial or neural maps per time point, and decomposing those maps, again, based on the correlation with the independent variables. And then project your data into that shared space, into that space that's going to maximize the covariance. And now instead of having to run one mixed effects model per feature per voxel and use up all your Amazon credits, we're just going to fit a single mixed effects model per component. And so that's going to be something like 20, 30, maybe if you've got a whole bunch of subjects, 100 mixed effects models that you're fitting, as opposed to fitting 10,000 or 100,000, depending on the resolution of your scan. So it's way, way faster. Again, it's the time for computing MELD is going to scale with the number of subjects. Time for computing a voxel-wise mixed effects model is going to scale with both the number of subjects and the number of features that you're trying to model. So we get the parameter estimates from component-wise mixed effects models run with LME4, and then we can reverse the singular value decomposition or go back through the singular value decomposition and project those from component space back into feature space. And that gives you, your map of these corrected, these parameter estimates that are correctly accounting for fixed effects and the item and subject level effects in feature space. And so to evaluate this, we just kind of did some simple proof of concept evaluation simulations. This data with a 100 by 100 noisy field with signal added to these little blips around. So you've got distributed pattern of signal, and we're testing this on a whole bunch of different levels of effect size, subject level variance, and item level variance. And I'm just going to show the correlation between the results that you get out of LME4 and the results that you get out of MELD to try to convince you that MELD is producing a reasonable approximation of the results from LME4 in a much shorter amount of time. And so there's a lot going on in these plots. I'll walk you through them. Up here, we've got increasing amounts of subject variance. This first column is the completely unrealistic case in which all of your subjects are the same, but it's a good starting point. And then going down the rows, we've got increasing amounts of item level variance. So that you're drawing your stimuli from progressively more variable populations. And then here, the lines are showing for various effect sizes. So no effect, effect size of 1, effect size of 4. What is the correlation across a whole bunch of simulations between the results from MELD and the results from LME4 at a voxel level? And so these are the correlations for this whole field of simulated data. And these are quite high. Most of this data is noise. Most of the data in a neural analysis is noise. So this is kind of looking at what you would get overall. And yeah, both the betas and the t-values are going to give you really high correlation between MELD and LME4, unless you've got kind of the absolute, just ridiculous amounts of subject level variance. Because we're using this correlation across subjects or correlation within subjects to project into a shared space, if there's a whole lot of variance across subjects, that projection falls apart a little bit. So it falls off in performance at these really, really high levels of subject variance. If we instead focus on just these elements where we've actually added signal, the correlation is still pretty good, not quite as good, and again, it falls apart when you get these absolutely insane amounts of subject level variance. But on the whole, considering this is going to take 10 seconds for mixed effects analysis versus several hours for to fit a single LME4 model to every voxel in the brain, I think it's a reasonable approximation. And we're definitely going to do some more work trying to explore how we can determine significance in these models. Our first pass was permutation approach. The problem you run into permuting in a mixed effect space is if you permute items, then you're not accounting for subject level variance. Permute subjects, you're not accounting for item level variance. And then if you permute both and you've broken both relationships, that's not valid either. So we're going to look at doing a parametric bootstrap in the component space and projecting those results back out to feature space. There's potentially other approaches that we'll look into. Or if you're just happy to take the parameter estimates and don't feel like you're as tied to p-values as I think other people are talking about at this very moment, that's another way that you could potentially go. And all the code for this is up on GitHub, compmem/meld. I'm happy to talk about it with anyone who's interested afterwards as well. I'd like to thank the team over at the NIMH who helped me do all this work, my old PhD advisor, Per Cederberg, as well, and Charles Zhang from the machine learning team who helped me put together a lot of those figures explaining singular value decomposition and mixed effects and MELD. So happy to take any questions.